As promised, here is the supplemental lecture, optional lecture, with notes posted online as usual of what I call the essentials of solid state physics. As I say here, it's bare bones. It's the nickel tour. If you really want to understand the essence of this, you need to take a course in solid state physics, which we, of course, offer. Um, this is not essential for the course. This is just to aid in your understanding, give you a little bit more insight into some of the things we've seen. For example, like I've mentioned in class, um, this business here, when we looked at the energy diagram for gallium arsenide, this is the K vector down here. Why is it labeled in the way it is? What is this L and lambda and gamma and delta and X and so forth? Well, to understand that requires some knowledge of crystal physics, and that's what the intention of this lecture is for. Um, Most solids, the kind that are used in lasers, are crystalline structures. That means they have a degree of symmetry. There's a crystal lattice present, unlike something like glass, which is an amorphous solid. Amorphous means, as it says, without a clearly defined shape or form. And one of the important things about the crystal is that you could almost think of it as a masses connected by springs, a three-dimensional, sort of like a mattress. And what happens when you put a disturbance on one end or one corner of a spring system? Well, that disturbance can propagate throughout the entire crystal. So these lattice vibrations, they're called phonons. We'll look at them more and more as the course goes on. They could transport energy, and they are used in the determining the properties and the behavior of electro-optical systems. If you want a book on this, there's really nothing in our text, our optional text, but take a look at the class, a very good book by Charles Cattell, Introduction to Solid State Physics. You could take a course on solid state physics, as I mentioned a moment ago. This is usually the book that they use in the physics department for their undergraduate course on solid state physics. All right, so what are we doing? We're looking at crystal structures. Well, there are more crystal structures than we have any time or I have any intention of going over. There are basically 14 what are identified as Bravais lattices as possible structures for a crystal. To understand what's going on with what we're talking about here, we're just going to look at three of these three particularly, the cubic crystals. They're cubes, right? Each side has length A. It's called the lattice parameter. And there's a simple cubic, and with just four lattice points on top, four lattice points on the bottom, 8 lattice points. There's a body-centered cubic, which is the same as the simple cubic, except that it has this point in the middle. And there's a face-centered cubic, which is the same as the simple cubic, except that it has a point on every face. These are the three that we're going to concern ourselves with. Now, I've been using terms like crystal lattice and so forth. What exactly is a crystal lattice? Well, very simply, it's an array of points, such as what you see here in front of you, but not just any old array of points, an array of points where each point is indistinguishable from every other point. Obviously, what I drew here is a two-dimensional representation of a point lattice. You'd have to use your imagination as to what this would look like in 3 dimensions, that I don't think it's hard to do. I also, you notice I say on the bottom, I assume that the lattice extends to infinity in all 3 directions. Right? So there's no edge, for example, of this thing. It just goes on and on. And when I say each element is the same or indistinguishable from every other point, well, you look at this point and you look at this point, and if you realize that this crystal goes on for infinity in all directions, you realize there's nothing unique about this point as compared to any other point in the system, in the lattice. As I look around me, I see the same thing regardless of which way I look, so to speak. Maybe to help clarify that, let me show you something that is not a point lattice. This is not a valid point lattice. because just look at these 2 points. Clearly their orientation is different, right? There's a rotation that kind of takes you from this point to this point. So each point is not indistinguishable from every other point. So this does not qualify as a valid point lattice. So what I'm going to do from this point forward is we're going to assume that we have such a point lattice. Here's yet another valid point lattice here. A little bit different from the first one I showed you. Okay, but it still qualifies as a valid point lattice. Okay, once we have chosen a point lattice, we choose 3 vectors. I'm calling them A1, A2, and A3. Again, in 2 dimensions. I'm just showing you 2 of them. And I form what's known as the direct lattice vector, capital R, which is a linear combination of A1, A2, and A3, where N1, N2, and N3 are integers. The 3 vectors, A1, A2, and A3, define a volume, and that volume is known as a unit cell. As the integers, N1, N2, N3 are varied, that volume fills up the entire lattice. You notice it doesn't necessarily have to be the smallest volume. The point is, though, as you vary the integers, you can fill this lattice, and I think that's easy to see in this 2-dimensional example. As I move by integer increments from any point to any other point, I fill up the lattice for myself. Okay, there's no unique choice of these lattice vectors. Here's one example. Here's another example. Here's another example. Any of these are valid because, again, if you think about it, as you move from point to point, you fill up the lattice with these vectors. But of course, like with everything, some choices are simpler than others, right? As I mentioned, we are interested only in 3 of the typical unit cells, the so-called cubic unit cells, the simple cubic, the body-centered cubic, and the face-centered cubic. Take a look at that simple cubic. Here's the unit cell. You can count 8 lattice points. But notice this unit cell doesn't sit by itself, it's part of a crystal. So each point is shared by 8 other cells, right? There are going to be 4 on, take this point for example. There are going to be 4 cubes on the top and 4 unit cells on the bottom, all that share this single point. So here's the important thing. Yes, I look at this thing and I see 8 points, but then I realize that each point is shared by 8 other cells. Hence, here's the important idea. There's 1 lattice point per unit cell. Okay, very simply, the body-centered cubic, well, the same as the face-centered cubic, except, right, the same as the face-centered cubic in that I have these 8 corner points that are shared by 8 other cells. But additionally, I have this point in the middle here that's not shared by anybody, that sits by itself. So in this case, there are going to be 3 lattice points per unit cell. What about for the face-centered cubic? Well, just like for the simple cubic, these 8 corner points constitute 1 point per unit cell, but in addition, I have these points on the faces. There are 6 faces, but each face is shared by 2 unit cells, right? So 6 faces divided by 2 is 3, so that means there's 1 plus 3 or 4 lattice points per unit cell, okay? What becomes important is what we saw for the simple cubic, where there's 1 lattice point per unit cell. A unit cell where there's 1 lattice point per unit cell has a special name. It's called a primitive unit cell. Okay? The simple cubic structure then is a primitive unit cell, and it's always possible to make a primitive unit cell out of any of the lattices we've seen. I'll show you how to do it. I'll show you a construction technique in a minute. But for example, here's the body-centered cubic cell. Just take my word for it for the time being. One valid choice for a primitive unit cell is to take, as I've chosen the coordinate system you see right here, take as A1 along the x direction, A2 along the y direction, and A3 right up the diagonal middle of the cube here. So A3 is going to be A2, a unit vector x plus unit vector y plus unit vector z. That qualifies as a primitive unit cell. Those three vectors, A1, A2, sweep out a volume. Here's another choice. And as I said before, the choice for the vectors A1, A2, A3 are not unique, even for the primitive unit cell. Here's another for the body-centered cubic. I start this time at the body-centered point, and I go to this front left corner and this front right corner and then the rear right corner. And I've drawn for you here the volume that these three vectors sweep out. The expression for these three vectors, these are just names. It doesn't matter what you call them, but A1, A2, A3 are listed here for you. I'll let you take a look at that and convince yourself that these are valid representations for these three vectors. Now, you might recall, if you have three vectors and you know that these three vectors sweep out a volume, the formula, wherever you learn that in middle school or high school, whatever, for the volume swept out by three vectors is simply given by A1 dotted into A2 cross A3. And of course, you got to watch the sign of A2 and A3 because you always want to define a volume as a positive number, right? So you do what you need to do to make sure it comes out positive. But that's the volume of a primitive unit cell, or of any, not of any primitive unit cell, but of any three vectors. For the primitive unit cell, let me show you another choice for the body-centered cubic. See what I've done here is I've gone to, here's the cube in question, the blue one. I've gone to the rear left point, okay? And what am I doing? From that point, I go up to the body-centered point on the blue cube. I move over to the left, and I go to the body-centered point on the green cube, and I go to the back, to the rear, and I go to the body-centered point on the pink kind of cube there. Those two define a primitive unit cell. The three vectors A1, A2, A3 for this coordinate system are given for you here. Again, you can take a look at that. Let me show you something interesting. For the one, this unit cell, that primitive unit cell that we just considered with these vectors. I rewrite them here for convenience. Let's compute the volume. The volume of that cell is, well, you could just go through the math, turns out to be 8 cubed over 2. Now think about that for a minute. The simple cubic cell, which is a primitive unit cell, in other words, one lattice point per unit cell, has a volume 8 cubed. The body-centered cubic is not got to be careful, by itself is not a primitive unit cell because it has 2 lattice points per unit cell. But when I choose a primitive unit cell, the volume is 8 cubed over 2. Okay? So again, the conventional body-centered cubic had 2 points per unit cell with volume 8 cubed, but the corresponding primitive cell has 1 point per cell with volume 8 cubed over 2. I think you might be able to guess what happens with a face-centered cubic. Here's a face-centered cubic. Clearly, the volume of what you see here is, again, A cubed, if each side here is A. The primitive unit cell, though, we know, since for the face-centered cubic there are 4 points, if you recall, per unit cell, it means the primitive unit cell would have to have a volume of 8 cubed divided by 4. One such volume, or one such primitive unit cell that would do that for us, for example, is the one that you see here. I start with this rear left corner point. I come up to the face point on the left side. I go to the face point on the bottom. I go to the face point on the back. For this coordinate system, here are these 3 vectors, A1, A2, and A3. If I go and I compute the volume of that cell with the same formula, I get, sure enough, A cubed over 4. and I sketched in for you here what that volume looks like. So we have this oddly oriented volume, of which as volume A cubed over 4, so it's 1/4 the volume of this entire blue unit cell. Okay. How do I, I'm kind of just giving you here, I'm saying here, these vectors form primitive unit cells. How can I get something like this? How could I construct something like this? Well, there's a technique called the Wiener-Stitz method, and it's based on the following idea. Here's again a 2D lattice that we've looked at. This is clearly a primitive unit cell because there, in this two-dimensional example, I see four points per cell, but each point is shared by 4 other cells, so there's 1 point per unit cell. So yes, indeed, for this two-dimensional example, this is a primitive unit cell. But then again, so is this, right? Here's a unit cell that as I vary integers, I cover this entire crystal. And obviously, this one has only 1 point per unit cell. This is the basis on the method of constructing the primitive unit cell that works for us. And I said it's called the Wigner-Stitz primitive unit cell construction technique. I go to a point lattice. Here's a point lattice. I pick any point. So, okay, I pick that point for myself, right? And what I do now is I draw lines from this point to all of its nearest neighbors. So from here to here, from here to here, from here to here, so forth. And I've done it for you here. I've drawn a line from this point to its nearest neighbor. Okay, like that. Next, what I do is for the lines I just drew, I construct perpendicular bisectors. Remember what a perpendicular bisector is. It's perpendicular to the line I just drew, and it chops it exactly in half. So if I draw perpendicular bisectors, these are the green lines here. So for example, this line has this as its perpendicular bisector. This line here has this as its perpendicular bisector. You look at this and you see what I've done is I've defined an area in this two-dimensional example. This area constitutes a primitive unit cell. So the volume, if a three-dimensional example, I'll show you what this looks like in 3 dimensions. It gets a little bit harder to do in 3 dimensions, right? Because this is, as I say, a well-studied field. There's a wealth of information on all of this, but I'm just trying to give you the idea here. The smallest, I'll call it a volume, in this case in 2 dimensions is the area, but the smallest volume enclosed here, that is indeed the primitive unit cell. And as you move along integer-wise from point to point, you see you could fill up this entire crystal. Had I done this in 3 dimensions, what I would have found for a body-centered cubic, I have to, if I'm doing 3 dimensions, what am I doing it for? I'm doing it for a body-centered cubic cell. I would get something that looks like this. It's called a truncated octahedron. It has a great deal of symmetry with it, which is something we will exploit for ourselves, but self-organized here. And we'll come back to this in a minute. Okay, why do we care? Why are we doing this? What we're trying to do, in essence, now. Remember, we said at the onset that the crystalline materials occupy or exist on a very organized lattice, right? A crystal lattice and so forth. Yeah. What that is a 3-dimensional periodic structure, right? So really what I'm trying to do here is I'm trying to capture the periodicity of this structure. To be able to do that, to be able to define or identify, perhaps I should say, the periodic nature of a crystal lattice, I mentioned that capital R that we defined a moment ago is known as the direct lattice vector. Now I'm going to define something known as a reciprocal lattice. Okay? And I'm going to define it, and I'm going to do it, and so we're going to do that. I'm going to define it, and then I'm going to show you why, or you'll see why I defined it the way I did. Given this as the direct lattice vector, I define a reciprocal lattice vector with three vectors, b1, b2, b3, and once again, three integers, m1, m2, and m3. Big K here is known as the reciprocal lattice vector. And the reciprocal lattice vector elements b1, b2, b3 are obtained from the direct lattice vector elements a1, a2, a3 by indicated as shown here. In other words, for b1, I take the other two, a2 and a3. For b2, I take a3 and a1, and I take for b3, a1 and a2. Every one of them is multiplied by 2 pi over the volume of the primitive unit cell. Remember, that's what VP is. It's the volume of the primitive unit cell. The order of the cross products, of course, is chosen just to keep things positive for myself. Why do I want this? Why do I want a reciprocal lattice vector? Well, I'm trying to capture, as I said, the periodicity of a three-dimensional crystal. Remember, as we discussed in class, the wave function, right? The Schrodinger wave function for a plane wave function in this case, e to the j k dot r, right? If this is to exist as a periodic function, and we saw, we'll look at it again, if this is to exist as a periodic function because it exists in a periodic lattice, then this function ought to be a periodic function. In other words, when I replace little r with little r plus big R, the direct lattice vector, and of course I could just write it as such, these two, if this is a periodic function, this should equal to this, right? Well, the only way this could equal this is if e to the j k dot r is equal to 1, right? And that happens only for special values, for specific values of k, namely when little k equals big K. Okay, so we captured the periodic nature of this three-dimensional lattice with this reciprocal lattice vector. Why is it called a reciprocal lattice vector? Well, let me back up here for 1 second. What are the units of, let's say, A2 cross A3? Meters squared. What are the units of the volume? Meter cubed. So you see B1, B2, and B3 have units of 1 over meters, hence they're called the reciprocal lattice because their units are that of reciprocal meters as compared with the direct lattice, which of course has units of meters. And if you want to convince yourself, I've done it for you, but you could look in your leisure, the fact that this is indeed equal to 1 when little k equals big K. Put in the details, do the math, you see you wind up with e to the j, an integer multiple of 2 pi, which is indeed 1. All right, let's do a couple of examples since we've defined a reciprocal lattice. Suppose we have our simple cubic structure. Okay, here's our simple cubic. Here's our three lattice vectors. Go and compute the reciprocal lattice vectors b1, b2, b3, as I've showed you. Right? Again, just take for b1, a2 cross a3, and divide by the volume, which is a cubed, and multiply by 2 pi. b1 is 2 pi over a times x, a unit vector in the x direction. b2, 2 pi over a, unit vector in the y direction. b3, 2 pi over a, unit vector in the z direction. So, a simple cubic lattice with lattice parameter a transforms into a simple cubic lattice with lattice parameter 2 pi over a in reciprocal space. Suppose we do the same thing for a body-centered cubic. Here are the three lattice vectors for the primitive lattice, primitive unit cell for a body-centered cubic. I go and use the formula I gave you for compute B1, B2, and B3. Here's what I get this time. And if you look back, you'll see that these are the lattice vectors for a face-centered cubic structure. Okay? So put it in words. a body-centered cubic lattice with lattice parameter A transforms to a face-centered cubic lattice with lattice parameter 4 pi over A in reciprocal space. I'll let you guess, I'll show you the result, but I'll let you guess what happens when you take for your direct lattice a face-centered cubic. In reciprocal space, it's going to be a body-centered cubic. And indeed, here is a face-centered cubic unit cell. Here are the three lattice vectors for the primitive unit cell. I'll let you go ahead and compute B1, B2, and B3 for yourself. And this is a body-centered cubic. So once again, in words, a face-centered cubic lattice with lattice parameter A transforms into a body-centered cubic lattice with lattice parameter 4 pi over A in reciprocal space. Okay, the big question, now that we're talking about all this well, crystal structure and so forth, crystal physics if you like, why do we care about such things? Well, as we've mentioned, and perhaps you're familiar, I don't know, you'll know it now, right? The primitive lattice in reciprocal space has a special name. It's called the Brillouin zone. Remember again, we're talking about a periodic array of a crystal, a periodic array of points that the wave function exists in. And for Schrodinger's equation, a periodic lattice has a periodic potential. So the potential energy for the crystal, V of R, is a periodic function. That makes sense. If it's a crystal structure, three-dimensional crystal structure that in principle extends to infinity in all three directions, I should see a periodic function for the potential energy of this thing. And so indeed we have. The solution to Schrodinger's equation, when we have a periodic potential, takes on a special form. Here's the wave function. It has the usual kind of plane wave component, e to the j k dot r, but as a coefficient, it has a function known as a block function, and the nature of this block function is such that it is periodic. U of little r plus big R is the same as U of little r. So what this becomes then is if we take our wave function, our Schrodinger wave function, right, and examine its periodicity, what we see is what we would expect to see. If we take the wave function, replace little r with little r plus big R, and then substitute and do the math, we see we get our, as we should for a periodic function, right? We get our same wave function back again times a phase shift factor, right, of e to the j k dot r. So in words, the wave function in one primitive cell in reciprocal space, i.e. in one of the Brillouin zones, differs by the wave function in any adjacent Brillouin zone by the factor e to the j k dot r. And you get from one Brillouin zone to some other Brillouin zone by varying this direct lattice vector r. That's what has you travel. That's what has you travel across the whole crystal. Okay. But notice or recall, there's that special value of k. When little k equals big K, we get that e to the j big K dot big R is equal to 1. We showed that already. Okay. The whole reason I did this is so that I could now do the following trick. I'll call it a trick, because in a sense, you take an arbitrary value of k and express it in terms of a reciprocal lattice vector plus whatever you need to make these two things equal. And I'll call that whatever I need to make up, k prime. Because if I do that, right, watch what happens. By our previous result, we found that the wave function is periodic in R. We get this additional phase shift factor. Right? If I express the k, as I'm suggesting here, with k prime plus big K, okay, well, e to the j big K dot big R is equal to 1. So this thing reduces to e to the j K prime dot big R times the original wave function. So compare. Our previous result said that I take the wave function and I move to some adjacent cell, I get the phase shift, e to the j K dot R. But I just showed you that if I take the wave function, move to the same adjacent cell, so these two are equal, this also equals e to the j K prime dot R. In other words, by doing this trick, I'm able to capture what happens in any Brillouin zone, anywhere, in terms of what happens in the first Brillouin zone. In other words, replacing k by k prime makes no difference. K and k prime yield the same wave function for values of k and k prime which differ by the big reciprocal lattice vector k. Maybe a picture will help. 2 dimensions again to make the drawing simple. We're going to really explain what this is intending to explain. We're going to have to go to 3 dimensions, but let's get our understanding here in 2 dimensions. Recall this picture, 2-dimensional. Here's our first Brillouin zone, this octagon that I show you here. Suppose for a k vector, I just pick this one, some far away, like that. So notice what I'm doing for my construction. Here's my k vector, right? I take a big K vector, which basically goes to the nearest lattice point. The difference between these two is K prime. But this vector gives me the same result as I would get from this vector. In other words, all I've done is taken this K prime vector, slid it back to here, and I get exactly the same thing. So to know what's going on out here, I could figure that out from what's going on inside the first Brillouin zone. This is the important piece of information in a certain sense, or the important idea, in that anything, because it's a periodic crystal, this is very intuitive. It's just that it gets a little bit cumbersome to explain mathematically because we're now talking about 3 dimensions. But you know that if you truly have a periodic function, once you know what's happening in one period, you know what's happening in every period. That's the whole nature of a periodic function, right? If I give you the information about one period, you've got it all. The same thing here, that's all this is, except it's now in 3 dimensions, so it's cast in a little bit more complicated thing. So what's going on out here can be explained with what's going on here. Same thing if, this K prime vector, then if I slid it out here so that it was on this lattice point here, this is an adjacent Brillouin zone. What's going on here is the same as what's going on here. So it's saying is that very intuitive result that you know well, that once I describe what's going on inside one period of a periodic function, I know what's happening in every period of that periodic function. Okay. Perhaps the only word of caution is that when you're computing energy, clearly K prime and K are 2 different vectors. So when you're computing energy, you can't use K prime to compute the energy. You got to use K. Okay? But in terms of all the other behavior, many values of K, anywhere in the crystal, can be represented by some value of K prime in the first Brillouin zone. Maybe to make it perhaps too simple, let's look at a one-dimensional example. Okay, that's about as simple. And one dimension is, of course, what you're familiar with in periodic functions, right, from math and so forth. You probably have I'm sure you've all looked at periodic functions in 1 dimension. So, okay, here's our one-dimensional crystal lattice with lattice parameter A. There isn't a whole lot of choice for the lattice vector. It's simply the lattice parameter times a unit vector in the x direction. Right? The reciprocal lattice vector, the reciprocal lattice vector, e to the j K dot R has to equal 1, as I'm showing here. K is an integer times the reciprocal lattice vector B. There's just 1 in this case. You multiply by 2 pi over the volume, but the volume in the one-dimensional crystal is just the lattice parameter A. Okay? Put in the integer, and of course it's going to have to be in the x direction again. So the reciprocal lattice vector is this, 2 pi over A times x. You can't get much simpler, maybe too, as I say, too simple in one direction. If I wanted to find my first Brillouin zone, remember the construction technique for doing that. Again, it's trivially simple. Pick this point, for example. Draw lines from this point to its nearest neighbors. There you go. Make perpendicular bisectors. Here's your first Brillouin zone. Okay, here inside these perpendicular bisectors, this line inside the perpendicular bisectors. If I wanted to know then what's happening for some value of k way out here, all I got to do is bring it back by, I probably should have an integer in there. I have big K. Clearly I'm moving by more than one integer. I should put some m in there. I move it back by some integer value of big K vectors. What's happening here in the lattice can be just as well described by what's happening at this point inside the lattice. So you could get the behavior here by the behavior, once again, inside the first Brillouin zone. I don't want to re-record this whole thing, so when I post these notes, the PDF of them, the recording is going to be this recording, but I'm going to stick an integer here because I really should have had one and I just carelessly forgot it. Okay? So that tells us that when we look at our energy diagrams, and for example, for a free electron in a one-dimensional lattice, we should, by this point, be familiar with, here's what the energy looks like, h bar squared k squared over twice the mass over 2m. Here's the first Brillouin zone, here's the second Brillouin zone, here's the third Brillouin zone, here's, if you like, the -1 Brillouin zone, the -2 Brillouin zone. What this information is telling me is that information that's going on in this second Brillouin zone, what did I go? I call this is the first, this is the second, this is the third. Is that what I call it, I hope? What's going on in this second Brillouin zone should be deducible or calculated from what's going on in the first Brillouin zone. And how do I do that? I take what's happening in the second Brillouin zone and I translate it to the left by a value of the k vector, like that, k1, 2 pi over n. Okay. Similarly, what's happening in this third Brillouin zone, I could figure out from the first Brillouin zone by taking this action here and moving it over by 2 times 2 pi over a to that. So in other words, 4 pi over a. Similarly, I could take all the action in the -2 Brillouin zone, move it over like that. I take this one here, move it over, and here we go. All k-space information is contained in the first Brillouin zone. Okay? So all the values of k here in the yellow are your values of k prime, but you got to remember to add on your k1 or your k2 when you're computing the energy. See, that's automatically happening with the way I constructed this image, because this is already elevated up. So when I move it over, that all works. So I don't need, again, very intuitive result, because the wave function exists on a crystal with a periodic potential. The wave function itself is a periodic function. If I know what's happening inside one period, that period is called the Brillouin zone, in this case the first Brillouin zone. I know what's happening in every other period, and that's what this diagram is capturing for us. Okay. Now here comes the big question. What about for 3 dimensions? Well, let me not be anywhere near as detailed, but simply give you some results. Once again, this is so well studied that even if you don't go to a book or take a course, you could Google these ideas, and believe me, you'll be inundated with information about this. I kind of already showed you, if I take a body-centered cubic, and here's a body-centered cubic with the lattice vectors that I showed you, the reciprocal space, the first Brillouin zone gives us this truncated octahedron. Look at me for a minute in the camera. Here's a truncated octahedron, right? You notice it's a wooden one. It's a truncated octahedron. Notice that there's a great deal of symmetry here, right? I have a hexagon here, and a hexagon here, and a hexagon here, and here, and here. I have a square here, I have a square here, I have a square here. The large degree of symmetry that exists for this tells me that I don't need to worry about this entire truncated octahedron. Like we've discussed in the past, all the information I need would be contained in the first octant of this thing. And I think as you look at this thing, you realize that. In other words, now let's go back to our picture on the slide here. The gamma point is always defined as the center point, the zero, the origin, in K-space of the first Brillouin zone. Whether I go from the origin to the center of this square, or the center of this square, or the center of this square, or the squares on the squares in the back that you can't see, and so forth, it's really, because of the symmetry, it's going to give me the same behavior. So instead of having to look at this whole thing, let me just look at the first octant of this thing, and that's what I have here. Okay, and now what I need to do is, so in other words, for all intents and purposes, this point and this point and this point on these squares are the same point. So in other words, this point, this point, this point are the same point in terms of the behavior of the wave function on the crystal. So we've named gamma, we need to name some of these points. And I guess people in the physics community who first studied crystals named these. I'm not sure why they chose the names that they did. Maybe somebody wants to explore the history and you could educate me. But for example, as you go from the origin, as I said, which is always called the gamma point, to the middle of the square face, that's called the x point. Why it's an x point, I don't know. But the point of the matter is that this is an x point, this is an x point, this is an x point. It's not seen, but there's an x point behind the thing here, and here there are lots of x points on this thing, right? I think there are 8 of them, which is why it's called an octahedron. On our octant diagram, in other words, then this is an x point, this is an x point, this is an x point. If you were to go from the origin right up the diagonal to the center of the hexagon here, that point right in the middle, that's called an L point. So this is an L point, this is an L point, this is an L point, here it is here. This is an L point. The place where the hexagon and the square meet there in the middle, that's called the K point. Okay? So there's a K point where the I've labeled some other points here. Okay? Am I forgetting to say anything here? No, I think I've said everything that's written in words here, so you've got it all. Now it's a matter of doing some of the calculations that we did with the either the one-dimensional, or we really did the one-dimensional case just a moment ago, right? We need to do it with this three-dimensional first Brillouin zone in reciprocal K-space. So we need to write some vectors. Okay, here's that first octant again. I don't know how much I need of this to belabor for you, but for example, if I wanted to describe the K vector that goes from the origin, namely the gamma point, to the x point, so there's an x point, there is an x point, there is an x point. This one in particular simply runs along the kx axis. So the k vector corresponding to x is 2 pi over a. That's because the length of this in the reciprocal space is 2 pi over a times a unit vector in the kx direction. Okay. What about L? L is the k vector that goes from the origin, the gamma point, up to the center face of this hexagon. So you do the geometry. It's 2 pi over a times 1/2 kx, 1/2 ky, 1/2 kz unit vectors. Kx unit vector, ky unit vector, kz unit vector. We can go on like this. If we wanted to go from the origin to the w point, 2 pi over a along the x direction, and we are only halfway, as it's coming right along the bottom of this thing, right? This bottom plane here, the kx, ky plane, you're running a vector from the origin to w. So what are its components? 2 pi over a in the kx direction, and halfway over, 1/2 2 pi over k in the ky direction. So there you are for the w point. Similarly, for the k point here, that goes along the bottom plane, and you see as you go from the origin to the point where, this is the point where center point of this face of the hexagon, that's 3/4 of the way here and 3/4 of the way here. So there's a k point. Okay, now that we have all these values of k, we are represented by. Now you're starting to see, I guess, what these points are, right? When I showed you that strange-looking diagram in class with a gamma point and an x point and a w and a k and an l and a k and so forth. What did that mean? Now you're starting to see what that means. That's the whole purpose of me doing this particular lecture for you. If we wanted to now compute the energy, it's a symmetric structure, so you need to, these things could get complicated fast. So no need to plot negative value. This is the first Brillouin zone, and here's the value of k prime and the first, but only the positive values of k prime. No need to plot the negative values because it's symmetric. I just take the mirror image, I flip it over, and I have the same thing, right? So the energy is h bar for a free electron, h bar 2 pi over m, magnitude k squared, and k, this k, of which we're taking its magnitude squared, is k prime plus big K. K prime is the part of that vector which lies in the first Brillouin zone. To capture information outside the first Brillouin zone, I add on big K, and big K has whatever integers are necessary to be able to give me the number that I want. And of course, I would now, if I wanted to go along this axis from here to here, what is the length of this? Remember, this goes from 0 to pi over a. Here, this is pi over a, and this is 0 to minus pi over a. So the Brillouin zone goes from the width of it is 2 pi over a. Right? So for k prime, I would put a parameter in alpha that I vary 2 pi over a times a unit vector in the x direction, and I let alpha go from 0 to 1. Okay, in which case I get I can take any value. I get any value along here, and when I do that and plot that in the energy here, here's what I get for different selections. I didn't label them because I'm not going to ask you to do this. People in the physics community start to call these diagrams spaghetti diagrams. Any idea why they may have the name spaghetti diagrams? It tells you something about how they start to look after a while. But each line here that you see is for a different set of integers. The first Brillouin zone, the second Brillouin zone, the M1, M2, M3. 0, 0, 1, 1, 1, 1, 2, 0, 0. You put in different values of integers. You have degeneracies very often. I could actually show you if you like. This one line might correspond to several different combinations of the integer m. That would be degenerate energies. But that's the idea. you could continue, do the same kind of thing. For example, suppose I wanted to go, as in the diagram that I showed you in class, right? Suppose I wanted to fill in the part that goes from X to W, and it goes through the midpoint Z. Okay, there's X, there's W, and it goes, so I want to vary K along this thick red line here. So in other words, I could express these values of K in terms of this X vector and this W vector. And I'm going to plot the energy normalized, make life simple. Instead of plotting the energy, I divided by h bar over 2n, just to make the numbers nice. Okay, always want to do that when you're making plots, right? So how could I do that? Well, again, what did I say? I want to go take the x vector and the w vector and use them to construct this xw vector. How could I do that? Well, here you go. Here's the x vector, x, right? Here's the w vector, w. If I do the following, if I let k prime be 1 minus alpha times x plus alpha times w, what happens? When alpha is equal to 0, I get this vector. When alpha is equal to 1, I get that vector. For values of alpha in between, I run along this line right here. Okay? So as I compute my energies, as I run along this line here, here's what I get. The first one, of course, is going to be for the first Brillouin zone, and then different values of integer m for the reciprocal lattice vector bring me to these higher and higher values of energy here for different combinations of integers. And again, there are degeneracies. So I would go on like this. For example, what did we see in class? I don't know that we have everything labeled in the same way exactly, but we went from the, what did we do here? Showing here, suppose we wanted to go, let's just do what I'm showing. We want to go from the origin along the bottom here to the K point, from the K point to the X point, from the X point to the W point, from the W point to the L point, from the L point back to the, or did I, back to the gamma point? I guess I could have just as well. Gamma to X, X to Z, X to W, W to L, L to gamma, then gamma to K, and then K to X. Okay? And I do, that's what I did here, right? First I did gamma to X, and I got that. And then I did X to W, and I got that. And I did those first two for you. Now I do all the rest, and I go from W to L, I get that. And then from L back to gamma, I get that one. And then from gamma to K, I get that one. And from K back to X, and I get that one. And I kind of squish all these together into one graph, right? And that's what you come up with. Again, this is for a free, I drew these for a free electron in a periodic crystal. This is not a free electron in a periodic crystal. This is an electron in a gallium arsenide, a gallium arsenide crystal, right? So it's different. It's a little more complicated for, as we're discovering in class. I also see the effects of the light, the heavy hole and the light hole and the spin-off hole and so forth. I don't know if we've talked about that yet, but if not, we certainly will. So anyway, that's it. This is what it's all about. When you see this, what at first looks like a strange looking diagram with how this x-axis gets labeled, I hope you see now that it's not, well, it is strange, right? There's no denying it. But now you understand, and now you understand the strangeness. Is that a better way to put it? You know why you see this. So this gives you an idea. As you advance in your studies of semiconductor physics, lasers, optoelectronics, and so forth, and you move on, you might want to take this to the next level. As I say, take a solid-state physics class and understand this a bit better. So that's it. Feel free to stop by my office if you want to discuss it further, or if you want to discuss this further in any way. I'd be happy to do that with you. But I hope this helps. I hope this gives you an idea, and I will see you in class.